All right, time to move to beams. We're going to look at forces in statically determinate beams and frames. By the end of this lecture, you should understand the internal loads on a beam, the internal loadings on any type of coplanar structure, but particularly focusing on beams and frames. Determine the shear and moment of a beam cross section at a specific point, and then as it varies along the length, and understand the relationship between the shear moment and the loading. Draw the shear moment diagrams for a beam and for a frame, and then use the principle of superposition to develop shear and moment diagrams for beams under multiple loadings. So let's say we're looking at a truss. We're just finished up trusses. And we've got this truss, and it has, if I cut it right here, and it has a compression load in this top chord and a tension load in the bottom chord and compression load in this diagonal. Notice they're equal and opposite on either side of where I've cut my truss using the method of sections. Okay? And I'm going to look at just the left side here. I'm going to draw those resultant forces, or those forces, member forces. So let's say I resolve this diagonal force into its horizontal and vertical components. So now if I sum the forces in the x direction, I should get some type of, and it's probably going to be that way, but some type of axial force. Right? If I sum the forces over the section, right, I'm going to get some type of axial force. I'm also going to get some type of shear force, right, that vertical force. Right? My vertical force is going to be a shear force. And I've got a tension on the bottom and a compression on the top. That would give me, that's a moment couple, right? Some D between the two. I'm going to have some type of moment. So if I look at the section of the truss as a complete cross section, not just as individual members, I notice I have three types of internal forces. An axial force acting along the length, which would be in the x direction in this case. A shear force acting perpendicular to that cross section, parallel to that cross section. The axial would be perpendicular. And then a moment caused by my coupled forces in the top and bottom chord. And that's basically what we're doing when we're talking about any type of cross section and moving on to beams. Now instead of individual members like the chords and the diagonals, we're going to have a complete cross section. Rectangular, T, circular, who knows what the cross section is, but it's going to be solid. It's going to have height and width, although still be mostly the largest dimension would be length for a beam. But the cross-sectional area would be considerably larger than the cross-sectional area, would likely be larger than the cross-sectional area that we're assuming for a truss, which only has axial force. So let's say I'm going to look at my internal loadings of my beam. Here I have my axial force. If I'm looking at, I take my beam and I cut a little cross section right here, right? I have an axial force, axial stress over that cross-sectional area, a shear stress, and then I likely also have, due to bending, that's a terrible shear, let me see, shear, and then due to bending, I also have moment stress, right? If you remember back to mechanics of materials, that's generally the distribution of normal stress resulting in a moment. That's looking at it in 2 dimensions. If I multiply by the width and I just look at the elevation view, right? Here and then now here. My stress distribution becomes a distribution along the height of the axial stress, the shear stress, and the stresses due to that result in a moment, right? With compression, this is bending with tension on the bottom and compression on the top. Then again, if I multiply that by the height, I can finally get a resultant of the axial stress, or the axial force. Actually, it's, which we designate as N because it is a normal force. It's acting normal or perpendicular to the beam cross section. I have a shear force, which we call V, and I have a moment. In this case, it's a moment where we have tension on the bottom and compression on the top, right? Tension, bottom. Right. If I were to take the resultant of that compressive stress, right, and the resultant of that tensile stress, there's some distance. That's my force couple, the distance between them. I get a moment. So, and there's my moment. And it's represented by the letter M. So this is just to show you that I'm going to talk about the internal loading, specifically force and moment. Force having the units of force, pounds or newtons. Moment, foot pounds, foot pounds, Newton meters. And this is, but they are resultant of the stresses that are acting on that cross section. Right. I'm just whittling them down from stresses to forces. So, And also note that this moment is about the centroid of the cross section. Okay? The sign convention that we are going to use for our internal forces or internal loadings is when I talk about my axial force. This is if I take a little chunk out of my beam, equal and opposite. This is the little chunk, right? This is my axial force, and tension is positive. If I look at my shear force, it's going to go down on that left side and up on the right side. And notice I do a half arrow because that's kind of just the nomenclature, how you draw it, kind of indicating it's acting on that surface. But equal and opposite, so that'd be up and that would be down if I'm looking at that chunk that I took out of there. A positive shear would rotate my little beam clockwise, right? If I apply those shear forces, it's going to rotate like that. And then finally we have our moment. That's my little half arrow. This is positive moment. It's called positive because it's happy. Right, see my little smile right there? It's also concave. Let's see, it holds water. I can say happy. It's positive bending. It means, it's mostly because, say we apply like a, right, generally we apply vertical gravity loads going down, and our displaced shape would look like that. So generally, when we're talking about beams, we're going to have positive bending due to the gravity loads. So how do I determine my internal loads at a certain point? First of all, I'm gonna solve for my if I'm given a beam with applied loading and unknown support reactions, I gotta calculate those. Then I'm going to cut my structure at the point where I want to determine my load. At the point. Draw a free body diagram of that section. of the cut section. Sorry, cut section. And on that free body diagram, I need to include my all applied loads, all support reactions, external loadings such as the any applied loads, concentrated forces, moments, and finally the internal loadings at that point. At the point of interest, I guess you could say. At the point of interest. And then finally just solve for those unknown internal loadings. Solve for the support reactions first, so that way the only thing unknown is your internal loading. And so you'll cut at that specific point, draw the free body diagram of the cut section, apply all of your support reactions, external loads, and then your internal loads at the point where you cut it, and solve for them. So I'm going to give an example here. I already solved for the support reactions. But let's say I want to know the axial load, shear, and moment at point C, which is at 2.5 feet from support A, and point D, which is right in the middle of this 10-foot long beam. First of all, I say our internal loads, we're not going to have any axial load because there's no horizontal forces. Therefore, my support at A, which is a pin, which would have a reaction. So therefore, right, my little therefore symbol. My reaction at A in the horizontal direction is 0, and N equals 0 along the length. So I'm going to ignore it, and we're just going to generally ignore axial forces in beams because beams are not there to be axially loaded. They can have an axial load within them, but they are there generally for shear and moment, for bending, flexure. Those are all words that you might hear, but yeah. The primary loads in a beam are shear and moment, not axial. Okay, so I'm gonna, let's see, I want to find it at C, so I'm going to cut my beam at C, right? And I'm gonna draw a free body diagram of everything to the left of C. So I'm gonna draw my applied load, my support, or I'm sorry, my reaction, my support, and my reaction at that support, and then there's no other applied load between the support at A and point C. So I've got my vertical reaction at A and then point C. So acting on that, I have my shear at C and my moment at C, right? So then all I have to do is solve for my unknowns. I don't know my shear, I don't know my moment. So sum of the forces in the y direction, because I only have one unknown, I can use that. I have my reaction going up. My shear at C going down, solve for that. Should get 42.5 pounds. I'm going to do the same for summing of the moments. I'm going to take the moments about the point at C. Right? So I have, like I said, I'm going to use positive as counterclockwise. So I have my 42.5 pounds. It's going to cause a negative moment because, right, that's negative, that's clockwise. So 2.5 feet times 4.25 pounds plus my moment at C. So my moment at C is 42.5 pounds times 2.5 feet, which should be 106.2 foot-pounds. Oops. Or pounds-feet, foot-pounds. Yeah. So my next one is I want to know it at D. So I'm going to cut it at D. So I need to draw everything. And really you could draw everything to the left or everything to the right. It doesn't matter. I'm going to draw everything to the left. But you could just take everything to the right. You know, say that this wasn't here and all you had is the one force. Well, it might be easier to just draw everything to the left. Just keep in mind your sign convention and go back and check it. If you, need to. So I've got my support, that 50-pound, right? My support, that 50-pound concentrated force, and then just my D. So, right, my 42.5 pounds at my support, my 50-pound concentrated force, my shear at D, and my moment at D. I'm going to pause for a minute, give you guys a chance to try this on your own. Might be a good idea to pause the video, try it on your own. See if you can get the right answer. I'm going to give you 2 minutes. If you need more than that, just pause it. Okay, I'm gonna continue on. If you need more time, pause it right here. So let's do the sum of the forces in the y direction. Acting up, we have 42.5 pounds. Down 50 pounds, right? Up, down 50 pounds. Also, oopsies, 50 pounds. Also acting down, we have our shear at D. So if I solve for that, I get 42.5 pounds minus 50 pounds, or negative 7.5 pounds. The negative just means I actually have shear acting in the upward direction at this point. It's just in the opposite direction of positive. Positive meaning downward. Similarly, I'm going to look at the sum of the moments at this point right here at D is equal to 0. So that 42.5 pounds is acting at 5 feet. It's acting up, so it is counterclockwise. I'm sorry, clockwise, which is negative. I've got my 5 pounds, which is acting at 5 minus 3 feet, so 2 feet, acting down, so it's counterclockwise. All right, 3 minus 2. 5 minus 3 is 2. And then I have my positive moment at D. If I solve for moment at D, I get 42.5 pounds times 5 feet minus 50 pounds times 2 feet. And that should give you 112 and a half feet, or pound. Foot pounds, pound foot, foot pounds. As long as you have foot and pound, it's fine. Okay? So let's do another example. This time I have, instead of that concentrated force, I have a distributed load. Other than that, it's the same. And again, I already solved for the reaction. So if you need help solving for reactions, let me know. And we can do an example. But you guys should have done that in mechanics of materials and statics. So internal loadings, again, gonna ignore that axial load. And I want to know at C, so I'm going to cut it, which happens to be not in the middle of, but in my distributed load. So let's do C together, and then I'll let you do D on your own. So let's see. I have C. I have my up, right, my reaction. I have my distributed load. And then I have my shear at C and my moment at C. And I'm going to solve for my internal loadings. Same exact way we already did it, right? Some of the forces at Y, positive. Acting up, I have my 33 pounds and my reaction at A. Acting down, I have, right here, I have what? 10 pounds per foot times 2.5 feet. That's the, right? My distributed load multiplied by the length. And I have my shear at C. Solve for the shear at C, and I get 33 pounds. Oopsies, that's a minus 10 pounds per foot times 2.5 feet. So my shear at C is 33 minus 25. So that is 8 pounds. Means it's acting downward. If I solve for the moment at C, let's see, I have 2.5 feet, 33 pounds. So that's acting counterclockwise. So 33 pounds times 2.5 feet. I have my resultant of my distributed load, the 10 pounds per foot times 2.5 feet, and it's acting at 2.5 feet over 2. It is acting counterclockwise, right? That's counterclockwise. So that's the force, right? And then the moment arm is 2.5 feet over 2. And I have my moment at C. So I solve for my moment at C. I got 33 pounds times 2.5 feet. Right, that's a 5. It kind of looks like a 3. Minus 10 pounds per foot times 2.5 feet. 2.5 feet over 2. If you wanted to already resolve that and make that equal to 25 before you put it in the equation, that's fine. I'm generally one that I write super long equations, but I only use like one equation as opposed to little steps on the way. That's just how I roll. Because I'm a nerd. And you get your moment at C is equal to 51.25 foot-pounds or pound-feet. Okay? I'm going to let you guys try D on your own. I guess in theory we could have also drawn the other side of the section, but I didn't, so you're gonna solve it this way if you want, or you could draw the other side of the section, right? But I got my shear at D and my moment at D. So I'm going to give you 5 minutes to try that on your own, and then I will work it out for you. See if you got the right answer. Okay, if you haven't finished it, I'd pause it right now. And we will figure this out. So let's see. I'm gonna take the sum of the forces in the y direction. I've got acting up, I have 33 pounds. Acting down, I have 10 pounds per foot over 3 feet, or 30 pounds. And I have my shear at D. If I solve for that, I get 33 pounds minus 10 pounds per foot times 3 feet, or 3 pounds. Now if I take the sum of my moments at D is equal to 0, I have acting at 5 feet and then up, so acting clockwise, which is negative. I have 33 pounds acting at 5 feet. I have this, which is 5 feet minus 3 feet over 2, minus 1.5 feet. So acting at that and then that direction, which is counterclockwise, which is positive. I have 10 pounds per foot times 3 feet times 5 minus 3 feet over 2, 5 feet minus 3 feet over 2. And then also acting in the positive direction, which is counterclockwise, I have my moment at D. So my moment at D is 33 pounds times 5 feet minus 10 pounds per foot, 3 feet, and the moment arm for that is 5 feet minus 3 feet over 2. And that should come out to 60 pound-feet. And that is how you solve for the internal loadings at a specific point. Right? You draw the section at the point of interest and make a free body diagram of the beam up until that point. And again, I could have at D, right? If I go back to D, it's right in the middle. I could have drawn this side, or I could have drawn this side. The one on the right doesn't have that distributed load, so it might have been a little bit easier, but it's always good to practice. So you could have drawn it either way. All right. And that is it for solving at a specific point.